We've now been on Mars for almost 2 months, and we've been witnessing the amazing new vistas of the never-before-seen Gale landscape taken with our wonderful cameras. However, much of the science team have had their eyes, and the rover's eyes, firmly focused on the ground. On the drive from the Bradbury landing site to our current location, we have been analysing 3 really interesting outcrops that we have called Goulburn, Link and Hotter. If we look at the Hotter outcrop, we can see a distinct layer that has been tilted and eroded, and this allows us to look at the cross-section through the layer. When we looked at the layer with our high-resolution Mastcam camera, we found that it was comprised of sand grains and small pebbles that had become cemented to form a hard layer. Here, you can see a pebble that is 3 centimeters in diameter, so smaller than a ping-pong ball. This suggests that this layer is an ancient gravel deposit. The surprising thing is that when we looked at the pebbles closely, we discovered that many of them were quite well rounded. This is very different to the many angular clasts that usually litter the Martian surface. Here, you can see a rounded pebble from a riverbed on Earth. On Earth, rounded pebbles are a common telltale sign of rocks that have been transported by water, for example in a river or a stream. As water flows over a riverbed, if the flow strength is great enough, the pebbles are lifted up into the flow or rolled along the riverbed, and they become pounded and battered against each other, and this causes them to become rounded through time. So what we think we might be seeing here on Mars is an ancient riverbed with the pebble beds representing old stream deposits. The size of the pebbles tells us that these rocks could not have been transported by the wind, so it seems clear they must have been transported by water. So how did this pebble deposit get to be here? If we look more broadly in Gale Crater, we can see that there is a prominent feature that geologists call an alluvial fan. Alluvial fans are cone-shaped deposits of gravel and sand that accumulate where streams exit mountains. In Gale Crater, there is a 10-kilometer long fan formed at the mouth of a 30-meter deep canyon that is derived from the crater rim. On the fan itself, we can see evidence for multiple channels suggesting that the stream bed direction changed through time. When we look at the location of the Curiosity landing site with respect to the alluvial fan, we see that the rover landed downstream of the fan. The rounded pebbles likely represent long-distance transport down the alluvial fan.
Curiosity is currently at the Rocknest location inside Gale Crater. When we first arrived at Rocknest, we performed a wheel scuff maneuver. This is our rover's version of kicking up the dirt with your hiking boot to determine if the Rocknest area was indeed a good first scoop target. The first scoop was successfully performed on Sol 61, and the entire team was excited to see the Mastcam images showing the scoop full of dirt, as well as the video of the vibration activities performed with the turret-mounted tools. This vibration allows the team to level out and remove any excess sample before closing the scoop, and it also provides some insight into the makeup of the soil. Any large particles would tend to float up to the top as the entire sample is vibrated, much the same way you would shake out the marshmallows in your box of Lucky Charms. Looking carefully at images, the team noticed a bright object lying on the ground just in front of the rover. We typically call something like this FOD, foreign object debris. The ChemCam remote micro imager captured a high-resolution image of the object showing that it is most likely a benign piece of plastic or shrink tube left over from a terminated wire. This could have possibly come from the rover or from the descent stage separation event during landing. Curiosity processed the scoop sample through Chimera, our labyrinth of passageways at the end of the arm that we use to sieve and portion the soil sample. We did some internal sandblasting by vibrating the sample at different orientations of the turret in order to remove any internal contamination. The team dropped the first scoop off to the left side of the rover, and in upcoming sols we will make our first attempt to drop off sample to the observation tray and the ChemIn instrument. We plan to be at Rocknest for the coming week to complete our scoop activities, and then we'll get back on the road to Glen Elg, where we'll be looking for our first rock to drill.
Curiosity continues scooping at Rocknest this week. The Mastcam and Navcam instruments provided images and video used to assess the success of the scooping and sample processing activities. These images also provided confirmation that the sampling system was successfully cleaned after the process was completed. Also this week, a soil sample was dropped off to the rover's observation tray for assessment by the science team. This sample was determined to be suitable for drop-off to the ChemIn instrument. The ChemIn instrument uses X-rays in order to image the sample and determine what minerals make it up. This helps geologists understand how the rock formed and how it's related to other rocks we've studied so far on Mars. Scientists identified numerous bright grains in the soil. Because of the small piece of plastic from the landing event that had been found earlier in the week, the team proceeded cautiously, dumping the second scoop collected and imaging the bright grains. These bright grains were later determined to be components of the Martian soil, and therefore the sample was deemed to be suitable for delivery to the Kemin instrument for analysis. The science team requested Mastcam and Navcam mosaics of the outcrops in the direction of Glenelg to plan Curiosity's journey to this next science destination.